two-dimensional geometric transformations. The basic geometric transformations are translation, rotation, and scaling. Other transformations that are often applied to objects include reflection and shear. Basic transformations. Here we first discuss general procedures for applying translation, rotation, and scaling parameters to reposition and resize two-dimensional objects. Later, we will discuss about how transformation equations can be expressed in a more convenient matrix formulation that allows efficient combination of object transformations. Translation. A translation is applied to an object by repositioning it along a straight line path from one coordinate location to another. We translate a two-dimensional point by adding translation distances tx and ty to the original coordinate position x, y to move the point to a new position x dash, y dash. The figure shows translating a point from position P to position P dash with translation vector t. The translation distance pair tx, ty is called a translation vector or shift vector. We can express the translation equations as follows. We can express these equations as a single matrix equation by using column vectors to represent the coordinate positions and the translation vector as shown on the screen. This allows us to write the two-dimensional translation equations in the matrix form. P dash equals P plus T. Sometimes matrix transformation equations are expressed in terms of coordinate row vectors instead of column vectors. In this case, we would write the matrix representations as P equals xy and T equals tx, ty. Since the column vector representation for a point is standard mathematical notation, and since many graphics packages, for example, GKS and PHIGS, also use the column vector representation. Translation is a rigid body transformation that moves objects without deformation. That is, every point on the object is translated by the same amount. A straight line segment is translated by applying the transformation equation P dash equals P plus T to each of the line endpoints and redrawing the line between the new endpoint positions. Polygons are translated by adding the translation vector to the coordinate position of each vertex and regenerating the polygon using the new set of vertex coordinates and the current attribute settings. This figure illustrates the application of a specified translation vector to move an object from one position to another. Similar methods are used to translate curved objects. To change the position of a circle or ellipse, we translate the center coordinates and redraw the figure in the new location. We translate other curves, for example, splines, by displacing the coordinate positions defining the objects. Then we reconstruct the curved paths using the translated coordinate positions. Rotation. A two-dimensional rotation is applied to an object by repositioning it along a circular path in the xy plane. To generate a rotation, we specify a rotation angle theta and the position x, r, y, r of the rotation point or pivot point about which the object is to be rotated, as shown in this figure. Positive values for the rotation angle define counterclockwise rotations about the pivot point, and negative values rotate the objects in the clockwise direction. This transformation can also be described as a rotation about a rotation axis that is perpendicular to the xy plane and passes through the pivot point. We first determine the transformation equations for rotation of a point position P when the pivot point is at the coordinate origin. The angular and coordinate relationships of the original and transformed point positions are shown in this figure. In this figure, r is the constant distance of the point from the origin, angle phi is the original angular position of the point from the horizontal, and theta is the rotation angle. Using standard trigonometric identities, we can express the transformed coordinates in terms of angles theta and phi as shown below. The original coordinates of the point in polar coordinates are x equals r cos phi, y equals r sin phi. We obtain the transformation equations for rotating a point at position x, y through an angle theta about the origin. X dash equals x cos theta minus y sin theta, y dash equals x sin theta plus y cos theta. We can write the rotation equations in the matrix form P dash equals R and P, where the rotation matrix is as shown on the screen. When coordinate positions are represented as row vectors instead of column vectors, the matrix product in rotation equation is transposed so that the transformed row coordinate vector x dash y dash is calculated as P dash transpose equals R and P transpose equals P transpose and R transpose, where P transpose x, y and the transpose R transpose of matrix R is obtained by interchanging rows and columns. For a rotation matrix, the transpose is obtained by simply changing the sign of the sign terms. Rotation of a point about an arbitrary pivot point is illustrated in this figure. Figure shows rotating a point from position x, y to position x dash, y dash through an angle theta about a rotation point xr, yr. Using the trigonometric relationships in this figure, we can generalize the transformation equation to obtain the transformation equations for rotation of a point about any specified rotation position xr, yr as shown below. Thus, the matrix expression modified to include pivot coordinates by matrix addition of a column vector, whose elements contain the additive translation terms. As with translations, rotations are rigid body transformations that move objects without deformation. Every point on an object is rotated through the same angle. A straight line segment is rotated by applying the rotation equations to each of the line endpoints and redrawing the line between the new endpoint positions. Polygons are rotated by displacing each vertex through the specified rotation angle and regenerating the polygon using the new vertices. Curved lines are rotated by repositioning the defining points and redrawing the curves. A circle or an ellipse, for instance, can be rotated about a non-central axis by moving the center position through the arc that subtends the specified rotation angle. An ellipse can be rotated about its center coordinates by rotating the major and minor axes. Solved example. Problem. Perform a 45-degree rotation of triangle A 0, 0, B 1, 1, C 5, 2 about the origin. Solution. We represent the triangle by a matrix formed from the homogeneous coordinates of the vertices as shown, and the matrix of rotation is as seen on the screen. So the coordinates A dash B dash C dash of the rotated triangle ABC can be found as thus A dash equals 0, 0, B dash equals 0, square root 2 and C dash equals 3 square root 2 divided by 2, 7 square root 2 divided by 2. Scaling. A scaling transformation alters the size of an object. This operation can be carried out for polygons by multiplying the coordinate values x, y of each vertex by scaling factors sx and sy to produce the transformed coordinates x dash, y dash as shown. Scaling factor sx scales objects in the x direction and scaling factor sy scales objects in the y direction. The above transformation equations can also be written in the matrix form as shown on screen, where S is a 2 by 2 scaling matrix or P dash equals S and P. Any positive numeric values can be assigned to the scaling factors Sx and Sy. Values less than 1 reduce the size of objects. Values greater than 1 produce an enlargement. Specifying a value of 1 for both Sx and Sy leaves the size of objects unchanged. When Sx and Sy are assigned the same value, a uniform scaling is produced that maintains relative object proportions. Unequal values for Sx and Xy result in a differential scaling that is often used in design applications where pictures are constructed from a few basic shapes that can be adjusted by scaling and positioning transformations as shown in this figure. This figure shows turning a square into a rectangle with scaling factors Sx equals 2 and Sy equals 1. Objects transformed are both scaled and repositioned. Scaling factors with values less than 1 move objects closer to the coordinate origin, while values greater than 1 move coordinate positions farther from the origin. This figure illustrates scaling a line by assigning the value 0.5 to both Sx and Sy. Both the line length and the distance from the origin are reduced by a factor of 1 by 2. This figure shows a line scaled using Sx minus Sy equals 0.5 is reduced in size and moved closer to the coordinate origin. We can control the location of a scaled object by choosing a position called the fixed point that is to remain unchanged after the scaling transformation. Coordinates for the fixed point xf, yf can be chosen as one of the vertices, the object centroid, or any other position as shown in this figure. This figure shows a scaling relative to a chosen fixed point xf, yf. A polygon is then scaled relative to the fixed point by scaling the distance from each vertex. Objects transformed are both scaled and repositioned. Scaling factors with values less than 1 move objects closer to the coordinate origin, while values greater than 1 move coordinate positions farther from the origin. This figure illustrates scaling a line by assigning the value 0.5 to both Sx and Sy. Both the line length and the distance from the origin are reduced by a factor of 1 by 2. Where the additive terms xf of 1 minus Sx and yf of 1 minus Sy are constant for all points in the object. Including coordinates for a fixed point in the scaling equations is similar to including coordinates for a pivot point in the rotation equations. We can set up a column vector whose elements are the constant terms in the above scaling transform equation. Then we add this column vector to the product S and P. In the next section, we discuss a matrix formulation for the transformation equations that involve only matrix multiplication. Polygons are scaled by applying transformations to each vertex and then regenerating the polygon using the transformed vertices. Other objects are scaled by applying the scaling transformation equations to the parameters defining the objects. An ellipse in standard position is resized by scaling the semi-major and semi-minor axes and redrawing the ellipse about the designated center coordinates. Uniform scaling of a circle is done by simply adjusting the radius. Then we redisplay the circle about the center coordinates using the transformed radius. Solved examples. Problem. An object is defined with respect to a coordinate system whose units are measured in feet. If an observer's coordinate system uses inches as the basic unit, what is the coordinate transformation used to describe the object coordinates in the observer's coordinate system? Solution. Since there are 12 inches to a feet, the required transformation can be described by a coordinate scaling transformation with S equals 1 by 12 or as shown on screen. And so, this yields the following result. Problem. Find the equation of the circle x dash squared plus y dash squared equals 1 in terms of xy coordinates assuming that the x-y' coordinate system from a scaling of A units in the x direction and B units in the y direction. Solution. From the equations for a coordinate scaling transformations, we find x dash equals 1 by A x, y dash equals 1 by B y. Substituting, we have the following equation. Notice that as a result of scaling, the equation of the circle is transformed to the equation of an ellipse in the xy coordinate system. Matrix representations and homogeneous coordinates. Many graphics applications involve sequences of geometric transformations. An animation, for example, might require an object to be translated and rotated at each increment of the motion. In design and picture construction applications, we perform translations, rotations, and scalings to fit the picture components in their proper positions. Each of the basic transformations can be expressed in the general matrix form, with coordinate positions p and p' represented as column vectors. P' equals m1 and p plus m2. Matrix M1 is a 2 by 2 array containing multiplicative factors, and M2 is a 2-element column matrix containing translational terms. For translation, M1 is the identity matrix. For rotation or scaling, M2 contains the translational terms associated with the pivot point or scaling fixed point. To produce a sequence of transformations with these equations, such as scaling followed by rotation then a translation, we must calculate the transformed coordinates one step at a time. First, coordinate positions are scaled, then these scaled coordinates are rotated, and finally the rotated coordinates are translated. A more efficient approach would be to combine the transformations so that the final coordinate positions are obtained directly from the initial coordinates, thereby eliminating the calculation of intermediate coordinate values. To be able to do this, we need to reformulate the above equation of the basic transformations to eliminate the matrix addition associated with the translation terms in M2. We can combine the multiplicative and translation terms for two-dimensional geometric transformations into a single matrix representation by expanding the 2 by 2 matrix representations to 3 by 3 matrices. This allows us to express all transformation equations as matrix multiplications, providing that we also expand the matrix representations for coordinate positions. To express any two-dimensional transformation as a matrix multiplication, we represent each Cartesian coordinate position x, y with the homogeneous coordinate triple xh, yh, h, where x equals xh over h and y equals yh over h. Thus, a general homogeneous coordinate representation can also be written as h.x, h.y, h. For two-dimensional geometric transformations, we can choose the homogeneous parameter h to be any non-zero value. Thus, there is an infinite number of equivalent homogeneous representations for each coordinate point x, y. A convenient choice is simply to set h equal 1. Each two-dimensional position is then represented with homogeneous coordinates x, y, 1. Other values for parameter h are needed, for example, in matrix formulations of three-dimensional viewing transformations. The term homogeneous coordinates is used in mathematics to refer to the effect of this representation on Cartesian equations. When a Cartesian point x, y is converted to a homogeneous representation, xh, yh, h, equations containing x and y, such as f of x, y equals 0, become homogeneous equations in the three parameters xh, yh, and h. This just means that if each of the three parameters is replaced by any value v times that parameter, the value v can be factored out of the equations. Expressing positions in homogeneous coordinates allows us to represent all geometric transformation equations as matrix multiplications. Coordinates are represented with 3-element column vectors, and transformation operations are written as 3 by 3 matrices. For translation, we have the following matrix. which we can write in the abbreviated form with T of Tx, Ty as a 3 by 3 translation matrix. P dash equals T of Tx, Ty into P. The inverse of the translation matrix is obtained by replacing the translation parameters Tx and Ty with their negatives minus Tx and minus Ty. Similarly, rotation transformation equations about the coordinate origin are now written as follows, or as P dash equals r theta into P. The rotation transformation operator r theta is a 3 by 3 matrix in the rotation transformation equations with rotation parameter theta. We get the inverse rotation matrix when theta is replaced with negative theta. Finally, a scaling transformation relative to the coordinate origin is now expressed as the matrix multiplication shown, or P dash equals S of Sx, Sy and P, where S of Xx and Sy is a 3 by 3 matrix with parameters Sx and Sy. Replacing these parameters with their multiplicative inverses of 1 by Sx and 1 by Sy yields the inverse scaling matrix. Matrix representations are standard methods for implementing transformations in graphic systems. In many systems, rotation and scaling functions produce transformations with respect to the coordinate origin. Rotations and scalings relative to other reference positions are then handled as a succession of transformation operations. An alternate approach in graphics package is to provide parameters in the transformation functions for the scaling fixed point coordinates and the pivot point coordinates. General rotation and scaling matrices that include the pivot or fixed point are then set up directly without the need to invoke a succession of transformation functions. Composite transformations. We can set up a matrix for any sequence of transformations as a composite transformation matrix by calculating the matrix product of the individual transformations. Forming products of transformation matrices is often referred to as concatenation or composition of matrices. For column matrix representation of coordinate positions, we form composite transformations by multiplying matrices in order from right to left. That is, each successive transformation matrix pre-multiplies the product of the preceding transformation matrices. Translations. If two successive translation vectors tx1, ty1 and tx2, ty2 are applied to a coordinate position P, the final transformation location P' is calculated as shown on screen, where P and P' are represented as homogeneous coordinate column vectors. We can verify this result by calculating the matrix product for the two associative groupings. Also, the composite transformation matrix for this sequence of translations is as shown here, or it can be stated as T of Tx2, Ty2 and T of Tx1, Ty1 equals T of Tx1 plus Tx2, Ty1 plus Ty2, which demonstrates that two successive translations are additive. Rotations. Two successive rotations applied to point P produce a transformed position P' equals r theta 2 multiplied by r theta 1 and P equals r theta 2 and r theta 1 multiplied by P. By multiplying the two rotation matrices, we can verify that the two successive rotations are additive. R theta 2 and r theta 1 equals r of theta 1 plus theta 2. So that the final rotated coordinates can be calculated with the composite rotation matrix as P' equals r of theta 1 plus theta 2 and P. Concatenating transformation matrices for two successive scaling operations produces the following composite scaling matrix. Or it can also be stated as S of Sx2, Sy2 and S of Sx1, Sy1 equals S of Sx1 and Sx2, sy1 and sy2. The resulting matrix in this case indicates that the successive scaling operations are multiplicative. That is, if we were to triple the size of an object twice in succession, the final size would be 9 times that of the original. General pivot point rotation. With a graphics package that only provides a rotate function for revolving objects about the coordinate origin, we can generate rotations about any selected pivot point xr, yr by performing the following sequence translate, rotate, translate operations. Translate the object so that the pivot point position is moved to the coordinate origin. Rotate the object about the coordinate origin. Translate the object so that the pivot point is returned to its original position. This transformation sequence is illustrated in the following figure. This figure shows a transformation sequence for rotating an object about a specified pivot point using the rotation matrix. The composite transformation matrix for this sequence is obtained with the concatenation as shown on screen, which can also be expressed in the form T of xr, yr and r theta and T of minus xr, minus yr equals r of xr, yr, theta, where T of minus xr minus yr equals T inverse of xr, yr. In general, a rotate function can be set up to accept parameters for pivot point coordinates as well as the rotation angle and to generate automatically the rotation matrix. General fixed point scaling. This figure illustrates a transformation sequence to produce scaling with respect to a selected fixed position xf, yf using a scaling function that can only scale relative to the coordinate origin. The figure shows a transformation sequence for scaling an object with respect to a specified fixed position using the scaling matrix S of xx, sy. Translate the object so that the fixed point coincides with the coordinate origin. Scale the object with respect to the coordinate origin. Use the inverse translation of step 1 to return the object to its original position. Concatenating the matrices for these three operations produces the required scaling matrix as shown on screen. Or it can also be stated as T of xf, yf and S of sx, sy and T of minus xf minus yf equals S of xf, yf, sx, sy. This transformation is automatically generated on systems that provide a scale function that accepts coordinates for the fixed point. General scaling directions. Parameters sx and sy scale objects along the x and y directions. We can scale an object in other directions by rotating the object to align the desired scaling directions with the coordinate axes before applying the scaling transformation. Suppose we want to apply scaling factors with values specified by parameters S1 and S2 in the directions shown in this figure. Scaling parameters S1 and S2 are to be applied in orthogonal directions defined by the angular displacement theta. To accomplish the scaling without changing the orientation of the object, we first perform a rotation so that the directions for S1 and S2 coincide with the x and y axes respectively. Then the scaling transformation is applied, followed by an opposite rotation to return points to their original orientations. The composite matrix resulting from the product of these three transformations is as shown on the screen. As an example of this scaling transformation, we turn a unit square into a parallelogram as shown in this figure by stretching it along the diagonal from 0, 0 to 1, 1. This figure shows a square converted to a parallelogram using the composite transformation matrix We rotate the diagonal onto the y-axis and double its length with the transformation parameters theta equaling 45 degrees and S1 equals 1 and S2 equals 2. We assume that scaling was to be performed relative to the origin. We could take this scaling operation one step further and concatenate the matrix with translation operators, so that the composite matrix would include parameters for the specification of a scaling fixed position. Concatenation properties. Matrix multiplication is associative. For any three matrices A, B, and C, the matrix product A and B and C can be performed by first multiplying A and B or by first multiplying B and C. A and B and C equals A and B, and C equals A and B and C. Therefore, we can evaluate matrix products using either a left-to-right or a right-to-left associative grouping. On the other hand, transformation products may not be commutative. The matrix product A and B is not equal to B and A in general. This means that if we want to translate and rotate an object, we must be careful about the order in which the composite matrix is evaluated in the figure. Reversing the order in which a sequence of transformations is performed may affect the transformed positions of an object. In A, an object is first translated then rotated. In B, the object is rotated first and then translated. For some special cases such as a sequence of transformations all of the same kind, the multiplication of transformation matrices is commutative. As an example, two successive rotations could be performed in either order and the final position would be the same. This commutative property holds also for two successive translations or two successive scalings. Another commutative pair of operations is rotation and uniform scaling, Sx equals Sy. General composite transformations and computational efficiency. A general two-dimensional transformation representing a combination of transactions, rotations, and scalings can be expressed as shown on the screen. The four elements Rsij are the multiplicative rotation scaling terms in the transformation that involve only rotation angles and scaling factors. Elements Trsx and Trsy are the translational terms containing combinations of translation distances, pivot point and fixed point coordinates, and rotation angles and scaling parameters. For example, if an object is to be scaled and rotated about its centroid coordinates x, y, and then translated, the values for the elements of the composite transformation matrix are as expressed on the screen. Although general two-dimensional transformation matrix equation requires 9 multiplications and 6 additions, the explicit calculations for the transformed coordinates are x dash equals x and rs xx plus y and rs xy plus trsx dash. Y dash equals y and rs yx plus y and rx yy plus trsy. Thus, we actually only need to perform 4 multiplications and 4 additions to transform coordinate positions. This is the maximum number of computations required for any transformation sequence once the individual matrices have been concatenated and the elements of the composite matrix evaluated. Without concatenation, the individual transformations would be applied one at a time and the number of calculations could be significantly increased. An efficient implementation for the transformation operations, therefore, is to formulate transformation matrices, concatenate any transformation sequence, and calculate transformed coordinates. On parallel systems, direct matrix multiplications with the composite transformation matrix can be equally efficient. A general rigid body transformation matrix involving only translations and rotations can be expressed in the form as shown on screen, where the 4 elements Rij are the multiplicative rotation terms and the elements Trx and Try are the translational terms. A rigid body change in coordinate position is also sometimes referred to as rigid motion transformations. All angles and distances between coordinate positions are unchanged by the transformation. The rigid body transformation matrix has the property that its upper left 2 by 2 submatrix is an orthogonal matrix. This means that if we consider each row of the submatrix as a vector, then the two vectors Rxx, Rxy, and ryx, ryy form an orthogonal set of unit vectors. Each vector has unit length rxx squared plus rxy squared equals ryx squared plus ryy squared equals 1. And the vectors are perpendicular. Their dot product is 0. rxx, ryx plus rxy, ryy equals 0. Therefore, if these unit vectors are transformed by the rotation submatrix rxx, rxy is converted to a unit vector along the x-axis, and ryx, ryy is transformed into a unit vector along the y-axis of the coordinate system, as shown below. As an example, the following rigid body transformation first rotates an object through an angle theta about a pivot point xr, yr, and then translates as shown. Here the orthogonal unit vectors in the upper left 2 by 2 submatrix are cos theta and minus sin theta, and sin theta, cos theta, and as shown below. Unit vector sin theta, cos theta is converted by the transformation matrix to the unit vector 0, 1 in the y direction. The orthogonal property of rotation matrices is useful for constructing a rotation matrix when we know the final orientation of an object rather than the amount of angular rotation necessary to put the object into that position. Directions for the desired orientation of an object could be determined by the alignment of a certain object in a scene or by selected positions in the scene. This figure shows an object that is to be aligned with the unit direction vectors u' and v'. In this figure, the rotation matrix for revolving an object from position A to position B can be constructed with the values of the unit orientation vectors u' and v' relative to the original orientation. Assuming that the original object orientation, as shown in part A, is aligned with the coordinate axis, we construct the desired transformation by assigning the elements of u' to the first row of the rotation matrix and the elements of v' to the second row. This can be a convenient method for obtaining the transformation matrix for rotation within a local or object coordinate system when we know the final orientation vectors. A similar transformation is a conversion of object descriptions from one coordinate system to another. Since rotation calculations require trigonometric evaluations and several multiplications for each transformed point, computational efficiency can become an important consideration in rotation transformations. In animations and other applications that involve many repeated transformations and small rotation angles, we can use approximations and iterative calculations to reduce computations in the composite transformation equations. When the rotation angle is small, the trigonometric function can be replaced with approximation values based on the first few terms of their power series expansions. For small enough angles less than 10 degrees, cos theta is approximately 1 and sin theta has a value very close to the value of theta in radians. If we are rotating in small angular steps about the origin, for instance, we can set cos theta to be 1 and reduce transformation calculations at each step to 2 multiplications and 2 additions for each set of coordinates to be rotated. X' equals x minus y sin theta, y' equals x sin theta plus y, where sin theta is evaluated once for all steps, assuming that the rotation angle does not change. The error introduced by this approximation at each step decreases as the rotation angle decreases. But even with small rotation angles, the accumulated error over many steps can become quite large. We can control the accumulated error by estimating the error in x' and y' at each step and resetting object positions when the error accumulation becomes too great. Composite transformations often involve inverse matrix calculations. Transformation sequences for general scaling directions and for reflections and shears, for example, can be described with inverse rotation components. The inverse matrix representations for the basic geometric transformations can be generated with simple procedures. An inverse translation matrix is obtained by changing the signs of the translation distances, and an inverse rotation matrix is obtained by performing a matrix transpose or changing the sign of the sign terms. These operations are much simpler than direct inverse matrix calculations. An implementation of composite transformations is given in the following procedure. Matrix M is initialized to the identity matrix. As each individual transformation is specified, it is concatenated with the total transformation matrix M. When all transformations have been specified, this composite transformation is applied to a given object. For this example, a polygon is scaled and rotated about a given reference point. Then the object is translated. This figure shows the original and final positions of the polygon transformed by this sequence, as shown below. Other transformations. Basic transformations such as translation, rotation, and scaling are included in most graphics packages. Some packages provide a few additional transformations that are useful in certain applications. Two such transformations are reflection and shear. Reflection. A reflection is a transformation that produces a mirror image of an object. The mirror image for a two-dimensional reflection is generated relative to an axis of reflection by rotating the object 180 degrees about the reflection axis. We can choose an axis of reflection in the xy plane or perpendicular to the xy plane. When the reflection axis is a line in the xy plane, the rotation path about this axis is in a plane perpendicular to the xy plane. For reflection axes that are perpendicular to the xy plane, the rotation path is in the xy plane. Following are examples of some common reflections. Reflection about the line y equals 0, the x-axis is accomplished with the transformation matrix, as shown on screen. This transformation keeps x values the same but flips the y values of coordinate positions. The resulting orientation of an object after it has been reflected about the x-axis is shown in this figure. This figure shows the reflection of an object about the x-axis. To envision the rotation transformation path for this reflection, we can think of the flat object moving out of the xy plane and rotating 180 degrees through three-dimensional space about the x-axis and back into the xy plane on the other side of the x-axis. A reflection about the y-axis flips x-coordinates while keeping y-coordinates the same. The matrix for this transformation is as shown on the screen. This figure illustrates the change in position of an object that has been reflected about the line x equals 0. This figure shows a reflection of an object about the y-axis. The equivalent rotation in this case is 180 degrees through three-dimensional space about the y-axis. We flip both the x and y coordinates of a point by reflecting relative to an axis that is perpendicular to the xy plane and that passes through the coordinate origin. This transformation, referred to as a reflection relative to the coordinate origin, has the matrix representation shown on the screen. An example of reflection about the origin is shown in this figure. The figure shows the reflection of an object relative to an axis perpendicular to the xy plane and passing through the coordinate origin. The reflection matrix is the rotation matrix r theta, with theta being 180 degrees. We are simply rotating the object in the xy plane half a revolution about the origin. Reflection can be generalized to any reflection point in the xy plane as shown in this figure. This figure shows a reflection of an object relative to an axis perpendicular to the xy plane and passing through the point P RFL. This reflection is the same as a 180-degree rotation in the xy plane using the reflection point as the pivot point. If we choose the reflection axis as the diagonal line y equals x as shown in this figure, reflection of an object with respect to the line y equals x. The reflection matrix is shown here. We can derive this matrix by concatenating a sequence of rotation and coordinate axis reflection matrices. One possible sequence is shown in these figures. A. Clockwise rotation of 45 degrees. B. Reflection about the x-axis. C. Counterclockwise rotation by 45 degrees. Here we first perform a clockwise rotation through a 45-degree angle which rotates the line y equals x onto the x-axis. Next we perform a reflection with respect to the x-axis. The final step is to rotate the line y equals x back to its original position with a counterclockwise rotation through 45 degrees. An equivalent sequence of transformations is first to reflect the object about the x-axis and then to rotate counterclockwise 90 degrees. To obtain a transformation matrix for reflection about the diagonal y equals minus x, we could concatenate matrices for the transformation sequence. Clockwise rotation by 45 degrees, reflection about the y-axis, and counterclockwise rotation by 45 degrees. The resulting transformation matrix will be as shown on the screen. This figure shows the original and final positions for an object transformed with this reflection matrix, as shown below. Reflection with respect to the line y equals minus x. Reflections about any line y equals mx plus b in the xy plane can be accomplished with the combination of translate, rotate, reflect transformations. In general, we first translate the line so that it passes through the origin. Then we can rotate the line onto one of the coordinate axes and reflect about that axis. Finally, we restore the line to its original position with the inverse rotation and translation transformations. We can implement reflections with respect to the coordinate axes or coordinate origin as scaling transformations with negative scaling factors. Also, elements of the reflection matrix can be set to values other than plus or minus 1. Values whose magnitudes are greater than 1 shift the mirror image farther from the reflection axis, and values with magnitudes less than 1 bring the mirror image closer to the reflection axis. Shear. A transformation that distorts the shape of an object such that the transformed shape appears as if the object were composed of internal layers that had been caused to slide over each other is called a shear. Two common shearing transformations are those that shift coordinate w values and those that shift y values. An x-direction shear relative to the x-axis is produced with the transformation matrix, which is shown, which transform the coordinate positions as x dash equals x plus shx and y dash equals y. Any real number can be assigned to the shear parameter shx. A coordinate position x, y is then shifted horizontally by an amount proportional to its distance y value from the x-axis y equals 0. Setting shx to 2, for example, changes the square in this figure into a parallelogram. Negative values for shx shift the coordinate positions to the left. This figure shows a unit square A is converted to a parallelogram B using the x-direction shear matrix with shx equals 2. We can generate the x-direction shears relative to the other reference lines with the matrix as shown below. The coordinate positions are now transformed as x dash equals x plus shx, y minus y ref, y dash equals y. An example of this shearing transformation is given in this figure for a shear parameter value of 1 by 2 relative to the line y ref equals minus 1. This figure shows a unit square A is transformed to a shifted parallelogram B with shx equals 1 by 2 and y ref equals minus 1 in the shear matrix. A y-direction shear relative to the line x equals x ref is generated with the transformation matrix as shown below. This generates the transformed coordinate positions as x dash equals x, y dash equals shy, x minus x ref plus y. This transformation shifts a coordinate position vertically by an amount proportional to its distance from the reference line x equals x ref. This figure illustrates the conversion of a square into a parallelogram with shy equals 1 by 2 and x ref equals minus 1. This figure shows a unit square A is turning into a shifted parallelogram B with parameter values shy equals 1 by 2 and x ref equals minus 1 in the y direction. Shearing operations can be expressed as sequences of basic transformations. The x-direction shear matrix, for example, can be written as a composite transformation involving a series of rotation and scaling matrices that would scale the unit square along its diagonal, while maintaining the original lengths and orientations of edges parallel to the x-axis. Shifts in the positions of objects relative to the sharing reference lines are equivalent to translations. Transformations between coordinate systems. Graphics applications often require the transformation of object descriptions from one coordinate system to another. Sometimes objects are described in non-Cartesian reference frames that take advantage of object symmetries. Coordinate descriptions in these systems must then be converted to Cartesian device coordinates for display. Some examples of two-dimensional non-Cartesian systems are polar coordinates, elliptical coordinates, and parabolic coordinates. In other cases, we need to transform between two Cartesian systems. For modeling and design applications, individual objects may be defined in their own local Cartesian references, and the local coordinates must then be transformed to position the objects within the overall scene coordinate system. A facility management program for office layouts, for instance, has individual coordinate reference descriptions for chairs and tables and other furniture that can be placed into a floor plan with multiple copies of the chairs and other items in different positions. In other applications, we may simply want to reorient the coordinate reference for displaying a scene. Here we consider transformations between two Cartesian frames of reference. This figure shows two Cartesian systems with the coordinate origins at 0, 0 and x0, y0, and with an orientation angle theta between the x and the x' axes. This figure shows a Cartesian x'-y' system positioned at x0, y0 with orientation theta in an xy Cartesian system. To transform object descriptions from xy coordinates to the x'-y' axis onto the xy axis. This is done in two steps. Translate so that the origin x0, y0 of the x'-y' system is moved to the origin of the xy system. Rotate the x' onto the x-axis. Translation of the coordinate origin is expressed with a matrix operation, as shown below. And the orientation of the two systems after the translation operation would appear as in this figure that follows. Position of the reference frames after translating the origin of the x'-y' system to the coordinate origin of the xy system is shown in this figure. To get the axes of the two systems into coincidence, we then perform the clockwise rotation, which is represented in this matrix. Concatenating these two transformations matrices gives us the complete composite matrix for transforming object descriptions from the xy system to the x'-y' system. mxy, x'-y' equals r of minus theta and t of minus x0, minus y0. An alternate method for getting the orientation of the second coordinate system is to specify a vector v that indicates a direction for the positive y' as shown in this figure. This figure shows the Cartesian system x'-y' with origin as p0 equals x0, y0 and the y' parallel to the vector v. Vector v is specified as a point in the xy reference frame relative to the origin of the xy system. A unit vector in the y' direction can then be obtained as shown below. And we obtain the unit vector u along the x' by rotating v 90 degrees clockwise, shown below. The matrix to rotate the x'-y' system into coincidence with xy system can be written as shown. As an example, suppose we choose the orientation for the y'-axis as v equals -1, 0. Then the x'-axis is in the positive y direction and the rotation transformation matrix will be as shown. In an interactive application, it may be more convenient to choose a direction for v relative to position p0 than it is to specify it relative to the xy coordinate origin. Unit vectors u and v would then be oriented as shown in this figure. A Cartesian x'-y' system defined with two coordinate positions p0 and p1 within an xy reference frame. The components of v are now calculated as v equals p1 minus p0 over modulus of p1 minus p0. And u is obtained as the perpendicular to v that forms a right-handed Cartesian system. Solved problems. Show the magnification of an object while keeping its center fixed. Let the geometric center be located at C, H, K. Choosing a magnification factor of S greater than 1, we construct the transformation by performing the following sequence of basic transformations. Step 1. Translate the object so that its center coincides with the origin as shown in the figure. Step 2. Scale the object with respect to the origin as shown here. Step 3. Translate the scaled object back to the original position as in this graph. Express as a composite transformation matrix, that is CTM, the transformation which magnifies an object about its center, C, H, K, from the previous example. The required transformation SSC can be written as SSC equals TV minus 1, SSS TV equals the matrix shown below.